PES, just some general terms that we're going to use today. The first is binding energy. So binding energy is the energy on the x-axis of a photoelectron spectrum. So the binding energy is what's on the x-axis. So when we talk about energy, we're going to be talking about the binding energy. This is also known as the ionization energy. Now we haven't actually talked about it in class yet. That's next week when we talk about periodic trends. But ionization energy is the energy required to remove an electron from an element. So when we're talking about energy today, we're really focusing on the ionization energy. How much energy does it take to remove an electron from an element? We're also going to be talking about nuclear charge a lot. We're going to focus on nuclear charge more, again, in periodic trends. This kind of transitions us from electron configurations to periodic trends. But nuclear charge is just the positive charge that's due to the protons in the nucleus. So when we're thinking about attraction between valence electrons and the protons in the nucleus, we're talking about nuclear charge. Nuclear charge ends up being our reasoning on almost all PES multiple choice questions. Because a lot of times, and I'm going to show you some examples of questions today and tomorrow. So tomorrow in the Do Now, we'll have another example of a multiple choice question with PES. But it's always asking, why is one peak further to the left or further to the right? Well, if you're talking about the peaks moving, that's the energy moving, we're talking about a difference in number of protons. So we're always going to be focusing on nuclear charge and number of protons. And then the last term is shielding. We used to talk about shielding a lot more, and then College Board kind of got rid of us using the term shielding in terms of a reasoning. So I do mention it sometimes. So the shielding effect just describes the attraction between an electron and the protons when you have more than one energy level. So if you have 3 energy levels between the nucleus and the valence electron, they're shielding that attraction. So if I had 2 magnets, right, so let's say I had these 2 magnets. Let's pretend these were a little bit more powerful. But when I bring 2 magnets together, right, they stick together. But imagine if I had stacks of paper between, they no longer stick together because the paper is shielding the attraction of the magnets. That's all that the shielding effect is. Again, we don't really use shielding as a reasoning anymore because College Board has wanted us to move completely to thinking about how the protons in the nucleus are attracted to the valence electrons. So we're just going to be talking about nuclear charge, and next week we'll talk more about Coulomb's law. So just some general terms just to help as we start talking about nuclear charge, or we start talking about binding energy or ionization energy. So for the most part, if there are questions on terms, it was these 3. And I have this is all part of the Do Now slides, so if you need to go back and reference the Do Now slides at all, I'll send the Do Now slides out to you guys again tomorrow since you guys are on Google Meet, so you can always go back and see them there as well. So these just were some different questions that I pulled right out of Edpuzzle. So I paraphrased them a little bit, but there were different questions on what we look at the spectrum for and how we look at the spectrum. So the first thing is that we are only going to be focusing on PES for neutral elements. We will not be looking at compounds, and we will not be looking at ions. So a question that I saw a lot was, what would a PES spectrum look like if we had a cation or if we had an anion? We don't worry about that because every atom is actually different based on the amount of energy that is removed. Transition metals removed from different energy levels. So we're only looking at PES for neutral elements. The PES graphs are organized by energy required to remove electrons. So they're organized by the binding energy. We will see all of the n equals 1 peaks together. all of the n equals 2 peaks will be close together. And then when we get into transition metals, we actually will see 3s, 3p, then 3d before 4s. And the reason that we have this peak, this is actually why we fill the 4s sublevel first. Those electrons are easier to remove, so they're technically lower in energy. I showed you what transition metal PES spectra look like. We actually don't, I have not seen a PES question yet that deals with transition metals. They are all main block elements. So main block means you're looking at something in the S and the P. There was a free response question that dealt with calcium, but essentially it looked exactly like this. So when you're looking at the peaks, and we're going to look at identifying the peaks in these examples, you're going to write it just like you would write a configuration. So if you go to 3p and then you notice that there's a next peak, that's actually going to be the 4s. It's just they're switched in energy because n equals 4 is further away from the nucleus than n equals 3. But just know that we will not be drawing, we will not be doing any work with transition metal PES spectra. You will be asked to draw basic PES graphs, and we're going to look at that in the examples, so like boron or carbon, and determine the electron configuration for, again, the main block elements, not transition metals. You also don't have to know specific energy values, so there were some questions about, am I going to have to label the binding energy? Am I going to have to know that somehow? No. Right, you're just going to look at relative, so like 1s should come before 2s, which should come before 2p, and so on. This is probably the most important thing on this slide. And whether you want to add it to your notes, somewhere we're going to be talking about it again in the examples, but PES is all about comparing the attraction between the electrons in different sublevels, so whether we're looking at the electrons in the 1s, or we're looking at the electrons in the 4s. We're always looking at the attraction between the electrons and the number of protons in the nucleus. So when we are looking at reasonings, any kind of reasoning for energy within PES, we should be looking at nuclear charge. So we should always be looking at how many protons are there in the nucleus. If there are more protons, it's a higher positive, so it's more attraction. If there are fewer protons, that's a lower attraction. So we're always going to be using the reasoning of nuclear charge, especially when we get to multiple choice questions regarding PES. This is something that College Board decided to put into the curriculum a few years ago, and I've seen a couple free response questions, but there are always lots of multiple choice questions that are related to PES. Okay, so those are different questions that I saw. If your question didn't get specifically answered now, it's because then I'm going to try to tie it into examples as well. So what we're going to do is we're going to go through practice. So like I said, we're going to do some of the practice together, and then I'll have you do a couple questions on your own. We'll check answers, and we'll kind of go back and forth. So essentially the last few pages in the notes are the video for practice. So this is the last part of chapter 6. I also, on Google Classroom, it was scheduled, I think, to go out this morning, there is something that's going to pop up that says extra practice. So if after we go through the in-class practice today, because mastering does not have any PES on it, if you think that you need more practice with it, I usually do a card sort in class where you guys have paper and you sort the configuration based on the spectrum, so then you can kind of move things around, but since we're not sharing things. I actually made an interactive card sort in Google Slides, so you can actually drag pictures to a spectrum, and I have the answer key as well in Google Classroom. So if you think that you want more practice with that, or if you want to do it tomorrow, like during the first period of class as a way to practice. That's in Google Classroom as well. And then you should have some time to work on mastering today. But we're going to focus on the practice first. Just a reminder for everyone, so you guys will be at home tomorrow. We're all going to take the Chapter 6 quiz at the same time. So it's going to push out to Google Classroom for your class at a specific time, so the beginning of second period. So the first period of class will be time to finish up mastering. So mastering is due by 2:30 tomorrow. If you're working on mastering today or this evening and have questions, send me questions. But the first period of class, we'll have it due now, and then you'll have more time to practice and review for the quiz. And then the quiz will start for everyone at the start of second period. So you guys will get back on the Google Meet if you leave. So you get back on at the beginning of second period, and then we'll take the quiz. So that's just kind of a little bit of looking ahead. So we're going to now get into the practice. So this is right out of your notes packet. I just pulled the notes packet up so that I could write on the board, just so that everybody at home can see it a little bit better, because my document camera apparently does not connect to my laptop well. So we're going to actually go through the first two questions together. So number one says, identify the element whose PES data is shown below. Now there are a couple of things that I want you to do for every PES question, no matter what. Start by looking at the x-axis, right? Because the x-axis is the energy. So the x-axis increases toward the left. Typically, it will increase toward the left, but not always. So you always want to start by looking at where is the highest energy. And then I always label on my spectra the highest energy. So highest energy is closest to the nucleus. So I always remember that the highest energy is closest to the nucleus, because then that tells me in my head, okay, that is the 1s. N equals 1 is closest to the nucleus. Before I even worry about these questions, I like to label all of the peaks, label the sublevels, because typically you're going to need to use that electron configuration for something. So this is closest to the nucleus, so this is my 1s. So in this case, each line represents an electron. But that's not always the case. I'm going to show you some different spectra. So if this is the 1s, if I see other peaks, that tells me that this sublevel is filled. So this is 1s2. What sublevel would I fill after 1s2? 2s2. And then 2p6. And again, I know that this is 2p6 one of two ways. One, I've now determined that each line represents one electron. So 1, 2, 3, 4, 5, 6. But I also noticed that I have a peak over here. So after 2p6 comes what sublevel? 3s. How many electrons do I have in this peak? Just one. Because notice, it goes up to the first line, but it's also half the size of 1s and 2s. Now you have the electron configuration. PES is just evidence for why electron configurations work. So A says identify the element whose PES data is shown below. So what element ends the configuration with 3s1? Sodium. So A is Na. Because all we do is we just use the electron configuration to identify the element. And then for part B, why is one peak so much larger than the others? So why is 2p so much bigger than 1s, 2s, and 3s? What does the peak tell us? How many electrons? All right, so our answer for this is there are more electrons. In 2p. There are more electrons in 2p than in any of the s sublevels, so the peak is higher. And then for C, so notice how by labeling the electron configuration, we were able to already have the configuration for A, and we're able to answer part C. So in which sublevel are the electrons represented by peak A? So what's the sublevel that we labeled here? 3s. That's, for the most part, it for PES. We're going to look at some additional conceptual questions together, like we're going to look at number 2 together. But really, that's PES. All right, just reading the graph to determine the electron configuration. Now we're going to look at number 2 together, because this is one of the conceptual type questions. And if it helps, I would actually recommend maybe putting just kind of a star next to number 2, because this is the type of multiple choice question. So MCQ, multiple choice question. This is the type of question that you would see as a multiple choice. Now obviously we're going to be just answering the question, but this is the type of question you would see for multiple choice. So this says the PES data shows only the peak for the 1s electrons. So I have nitrogen and oxygen. So this is the 1s for nitrogen, and this is the 1s for oxygen. Now I am going to add an arrow here. So I'm going to add the arrow pointing to the left. So over here is the highest energy. This is the highest energy. So why is the peak for nitrogen farther to the right? So I'm going to start. This is always how you want to start any kind of free response question, is start by kind of just saying nitrogen's peak is farther to the right, and then we'll answer the question. Okay, so let's first think about what this means. Nitrogen is further to the right. So nitrogen really is about here. That means that nitrogen's 1s peak is less energy. Less energy means it's easier to remove. So it's farther to the right because the 1s electrons are easier to remove. And then we want to think about why. So we gave the answer, but they always want the why as well. So nitrogen's peak is farther to the right because the 1s electrons are easier to remove. This is where it comes to thinking about nuclear charge. So when we think about energy and how easy or how hard it is to remove, we have to look at the number of protons. So look at the atomic charge, or the atomic number. Nitrogen's atomic number is 7. Oxygen's is 8. So nitrogen has an atomic number of 7. It has 7 protons. Oxygen has 8. So we'll say this is because nitrogen has fewer protons than oxygen. And in parentheses, I'll say 7 compared to 8. So, fewer protons means a weaker attraction between electrons and the nucleus. So a lot of times they like asking questions like this where you're not actually comparing the valence electrons, you're comparing the core electrons. You're comparing the electrons that are closest to the nucleus. So when you're comparing these electrons that are in the 1s, we're looking at how hard is it to remove them. Nitrogen's 1s is farther to the right, which means it's lower in energy. It's easier to remove. That's because nitrogen has fewer protons. So we're going to compare number of protons to look at the attraction. Okay, so what I want you to see if you can do is see if you can do 3, 4, and 5. Now, with number 3, I'll kind of draw the main outline for you. So 3 wants you to actually draw the expected PES spectrum for boron. All you really need is to label the x-axis as energy, and most people will draw it with the arrow pointing to the left. That means that the left is going to be closest to the nucleus. Here's a tip. If you need to write a PES spectra, write the configuration first. You should see a peak for each sublevel. So write the configuration for boron, and then use number 1 kind of as a guide. Write the spectrum in number 1. And then once you do number 3, also go through and answer 4 and 5. Hopefully your spectrum for boron you can check up on the board once you've drawn it. You don't have to label the peaks, but you have 1 peak for each sublevel. So 3 different sublevels means you should see 3 different peaks. Sodium in number 1 had 4 sublevels filled. That's why we saw 4 peaks. So the number of sublevels represents the number of peaks. But then number 4, we kind of answered that in number 1, which determines the height of each peak. So however many electrons you have in the sublevel, that determines the height. The more electrons in the sublevel, the taller the peak. So 5 is not asking about the height of the peak, it's asking about the number of peaks. So 5 says, why are the number of peaks in hydrogen and helium the same? So if you actually look at the spectrum of hydrogen and helium, they both only have 1 peak. Why do they both only have 1 peak?
They're both using the 1s sublevel.
They're both only in the 1s sublevel. So both only occupy the 1s sublevel. Now the height of the peaks might be different, but they both only have 1 peak. So if you flip to the next page, I want you guys to actually see if you can do 6 through 9. So 6, 7, you're identifying. 8 and 9, you're essentially identifying as well. Be careful in number 7, because it says the 1s electrons are omitted. So that means you're actually starting with 2s. Right, so in number 7, you're starting with 2s. So work through 6 through 9. As you work through, I'll put the answers up on the board so that you can check. And we're actually going to go through 10 and 11 together, because these are more conceptual style questions. And one part of 9 actually does go onto the back page. So once you're looking at that, there's the part C for 9 is on the back. I do want to just do 6 and 7 so I can scroll up to start putting the answers for 8 and 9 up. When you look at 6, again, notice energy, highest energy is here, so that's the 1s. And then I work my way through. I just drew a line across so I could tell that 3s2 was the same height. So that is identified as magnesium. And 7, again, it says the 1s electrons are omitted, which means we start with 2s. Right, 2s, 2p. Then we get to this part where if you write it like a configuration, something is a little off because you have 3s, 3p. Well, we know that 4s should only be the same height as 3s. So we have this big tall peak. That's because all of the n equals 3 is put together. So we go 3p, 3d, then back down to 4s and 4p. Again, heights are the same, so that tells us that it's 4p6. So when you look at 8 and 9, again, 9c goes on to the back of the page. So just make sure that you look at C that's on the very back. All right, if you check 8, group number, you could have one of two things. You could say 3A or 13. If you go based off of your periodic table now, the group numbers are labeled at the top. So if you did, most of you probably would have done group 13. Remember, group is a column. And then which element? Always use the electron configuration to identify the element. So I always label the peaks. That's the first thing I do before I even read the questions, is I label the peaks. Typically that's going to help us identify the element or write the configuration. So again, when you label the configuration, label the peaks. This peak is just slightly higher than the 3s, which is why it's 3p. It's about half the height of the 2p6. So when you look at 3s2, 3p3, look on the periodic table. I find 3s2, 3p3, that's phosphorus. Write the configuration. We already did it right here, so just rewrite it down here. 1s2, 2s2, 2p6, 3s2, 3p3. This is really it for identifying like PES. And then C. So C says, sketch the PES spectrum for an atom having 8 fewer protons. 8 fewer protons than atom X. So phosphorus has 15 protons. So 8 fewer protons is nitrogen, with an atomic number of 7. Z, if you don't remember, represents atomic number. You could write atomic number or number of protons and be fine. So all I'm going to do is I'm going to write configuration for nitrogen. 1s2, 2s2, 2p3. There's our configuration. Now just put that into a PES graph. So putting it into a PES graph, I'll have energy on the X. Again, this tells me my number of peaks. So 3 sublevels means 3 peaks. And then the exponents tell me my number of electrons in each peak. So I'm just going to do this to help me represent my number of electrons. So 1s2, then 2s2, then So in terms of sketching a spectrum, this is all we would have to do. You do it based on the electron configuration. We just find the electron configuration, number of sublevels. All right, so if that's something that you think you might forget, I'll just make a note here. Number of sublevels equals number of peaks. So the 1s, the 2s, and the 2p, that's 3 sublevels. We should see 3 peaks. So any questions on 6 through 9? Okay, so before the bell rings, here's what I want you to do with 10. I want you, so we're going to actually answer the questions together, but I want you to look at number 10, and I want you to see if you can just label the peaks on the spectrum. Just label the peaks using the electron configuration on the spectrum. So it tells us that the complete photoelectron spectrum of an unknown element is given above. So here's my energy. Here's closest to the nucleus because it's highest in energy, so that's 1s. So now I want you to focus on these lines. See how the lines now, each line doesn't represent 1 electron. Each line in this case actually represents 2. So here's our configuration. So we'll go ahead and go through number 10. So we already did the electron configuration. So again, I labeled closest to the nucleus, and then I labeled each peak. So A says, draw an X above the peak that corresponds to the orbital with electrons that are on average closest to the nucleus. So which of these sublevels, and I labeled it on the x-axis too, which of these sublevels is closest to the nucleus? 1s. So put an X. Then it says justify your answer. This is where we start to get into the true AP style free response, where you have to do something and then justify your answer. So it says justify your answer in terms of the attraction between the electrons and the nucleus. So we want to make sure we're talking about the attraction between the 1s electrons and the nucleus. So I'll just say the attraction between the nucleus, which is positive, and electrons, which are negative, increases as they get closer together. So as a positive and negative charge get closer together, opposites attract. So the attraction is going to increase as they get closer together. So I can say this is why the 1s electrons have the highest binding energy. Highest binding energy means they have the highest energy required to remove the electron. So when we're talking about highest energy here, we're talking about the amount of energy that's required to remove that electron. So notice again, we're talking about that nuclear charge. We're talking about the protons in the nucleus and the electrons. So the 1s electrons have the highest binding energy because the 1s electrons, if we think about the Bohr model of the atom, even though it's not correct, right, so we know now this isn't the best model, but the 1s electrons are here. They're much closer than, say, the 3s electrons. So since they're much closer, there's going to be more attraction between the protons in the nucleus and these electrons. So the nucleus is holding on to these electrons a lot more. So part B, based on the spectrum, write the complete electron configuration. Well, this is why labeling the peaks is useful. Because We already wrote the configuration. And then part C, on the graph, draw the peaks corresponding to the valence electrons. So I know now I'm going to be working with valence electrons, so the outermost electrons, of the element that has one more proton in its nucleus. One more proton in its nucleus than the unknown element has. So let's just kind of take this step by step. First, I need to know what the unknown element is. So based on this configuration, what's the unknown element? Sodium. Okay, so the unknown element is sodium. So now we're going to be looking at an element that has one more proton in its nucleus. Sodium has an atomic number of 11, has 11 protons in the nucleus. What is the element that has the atomic number of 12? Magnesium. So we are going to be drawing the peak that corresponds to the valence electrons of magnesium. Now this is going to be important because it has one more proton. That means it has a little bit stronger of an attraction to the valence electrons. Now Mg has 2 valence electrons. Magnesium, the configuration ends in 3s2. So I'm actually going to draw a peak right here. So it says on the graph, draw the peak. Now I'm going to put some information here if you want to write it down so when you're looking back, you remember. So I'm going to say the peak is a little to the left since magnesium has more protons. So the peak is actually a little bit to the left of sodium's 3s peak because magnesium has one more proton. So one more proton means the electrons are more attracted to Mg's nucleus, again because it has one more proton, making it slightly more difficult to remove. So since magnesium has one more proton, it's increasing the attraction between its nucleus and its valence electrons. Yes, we are adding one more valence electron, but we're also adding one more proton in the nucleus. More positive, more attraction toward the nucleus. So 10 and 11 are actually practice AP questions. So we're going through them together, practicing answering these. But notice again that we focus on the attraction between the protons in the nucleus and the electrons. That's essentially been our reasoning the whole time. So when we actually look at number 11, right, so when we look at number 11, freeze. So number 11, this is the last practice question. Number 11 says the PES data for the 1s sublevel of lithium and the 1s sublevel for sodium. So before I even continue reading this question, I want you to look at your periodic table, and above lithium, write the atomic number of lithium, and above sodium, write the atomic number of sodium, because that's the number of protons that are in their nuclei. So look at your periodic table. Lithium has an atomic number of 3. Sodium has an atomic number of 11. Atomic number. So the PES data for lithium and sodium are represented below. A student claims that element A is lithium. Do you agree with the claim? The first thing that you should answer is I agree or I disagree. And then you can continue on. And then it says justify your answer in terms of attraction between the electrons and the nucleus. So we're going to start with either I agree or I disagree, and then we're going to justify and we're going to say why based on attraction. So they think that element A is lithium. So it tells us that these are the 1s electrons for both. Remember, the more protons in the nucleus, the stronger the attraction to the 1s electrons. Which of the atoms has more protons in the nucleus? Sodium. Sodium has more protons, so it's going to have a stronger attraction. That means we should see the 1s electrons of sodium having a higher binding energy. Here's the one that has the higher binding energy. So based on this data, element A should be sodium, element B should be lithium. So you can go through, you can work through the problem like that and then actually answer the question. So it says a student claims that element A is lithium. Well, based on what we said here, do we agree or do we disagree? Disagree. So I'm going to say I disagree. That's how you want to start. That's how you want to start your answer. You always want to answer the actual I agree or I disagree or yes or no. Now we'll justify our answer. So lithium has 3 protons, while sodium has 11. It says justify in terms of attraction between electrons in the nucleus, so we need to make sure we talk about attraction. So the more protons, the stronger the attraction to the 1s electrons. So then I'm going to go on a little bit more and I'm going to say since lithium has fewer protons, the 1s electrons will be less attracted to the nucleus. And have a lower binding energy. So binding energy, again, is ionization energy. It's the energy required to remove an electron. This question, I would also star. This is another example of a multiple choice type question where you're comparing the 1s electrons, and look at our reasoning. It's between the protons in the nucleus and the electrons.